Suppose I should remove my tripping hazards before engaging in a video. Otherwise you're gonna see me visit the doctor. I'll live stream it, so all right. So it's been a while since we've had a lecture, in part because I've been busy, but in part because, quite frankly, we've been working on our project, and there's a lot of work to do on this project. So what I'm providing as a lecture this week is a discussion on the Pugh decision matrix. This all comes from chapter 8 in your book. And to kind of precedence this, we're going to go ahead and I'm going to go back to the fundamental idea of all problem solving. All problem solving involves 4 steps, okay? So problem solving, your 4 steps are: 1, identify the problem. 2, once you've identified the problem, you identify what you need the solution to look like. Here's what I need the final result to be. I like to use the example of I'm hungry. Final solution is I'm not hungry. But I'm also very, very motivated by food, so maybe I'm a little different. But another example would be identify the problem. Construction is a lot of problem solving. Let's say you have you've noticed that there's a weak spot in the roof where you feel like the roof is not very well supported, and you go look at that location, and according to the design, the roof truss diverges at that location. You may have a nearby ridge or valley or something that would ultimately prevent you from having a normal roof structure. So let's say you have this instance that occurs. Your problem solving process is, well, I need to reinforce this board. I need to do something to support it so that the board is no longer weak. And then you look at your options. So second step is identify requirements of solution. Your third step is to solve it. Do just anything to solve the problem. And then your fourth step is to determine if the problem still persists. Because if it does, then you have to go back to the first step. And we've done this problem solving process our whole lives. It's how you learn math. You write out the answer to a math equation, figure out, okay, did I do it right? Well, requirements of my solution. Problem is I get handed a math problem. Solution is I need to get an A. And then you solve the math problem, and then you hand it into your teacher and they grade it and hand it back to you. And most people will try to learn, look over what you did, try to understand the mistakes that you made, try to make adjustments, try to learn from mistakes, go back, solve the problem again, do it all over again. A lot of people will do that, and that's a problem. That is the proper problem solving process. The problem. Okay? And so ultimately, when we go to do any kind of problem solving, we need this. And the issue that we run into is this is not always very straightforward. If it's a problem where we can just simply it's gone once we've solved it, that's one thing. But if it's a problem where the problem persists, but it's at least better than it was before, sometimes that's really the best that we can do. And this is where the Pugh decision matrix comes into play, okay? Because it really helps us out with this fourth step, identifying whether or not the problem still remains and whether or not the problem is substantial enough that has anything gotten better as a result of our process. Not only that, but was our process itself worth making it better? Okay, you know, I could fund a roadway that goes straight from my house to Doane. Okay, that would involve paving, purchasing people's houses and farms, finding ways around it, building overpasses. I could do it. I could spend billions of dollars in infrastructure to get to work. And then I might be able to make the work 5 minutes faster. And then the question is it worth it? Like, yes, okay, gone through all this problem-solving process, solved it, problems better, yeah. Now, was the process of solving that problem actually better than the problem itself? No. I will drive 5 extra minutes and not spend $1 billion optimizing my route to work. And there's other factors that go into that, but I've thought about that often. Better way to work. Of course, Canon was one of my options. A lot cheaper, a little bit more dangerous, but showing up to work like full of adrenaline, I think I'd be a better teacher that way. In any case. So we're going to talk about Pugh's decision matrix. Now the book lays out the Pugh's decision matrix the same way it does for a lot of these things. It's got, first of all, you have a number of boxes that are created. The author labels them as the issue. And then down here you have a box that says criteria. And then you have importance. And then you have alternatives. Here's your evaluation. And here are your results. Now this is kind of a different way of approaching this. This actually makes it look a little bit more complex than it actually is. Let's go ahead and start with just an example here. So, screenshot of that if you like. I'll even do it like a Vanna White pose. There, screenshot that. Okay, so let's say we are, we're deciding on for my bike, let's say I'm planning on using an electric motor in my bike. Okay, so issue. I have to make a selection between different electric motors. Okay, I can't just grab like, well, that looks good. It doesn't quite work like that. There's actually a lot of design criteria that are needed in order to make a good decision here. So if this is my issue, that I need to select between different electric motors, then, well, that's my issue. That's step one of the Pugh matrix process. That's step one. Step two is coming up with alternatives. Okay, so let's say I've got 3 motors that are relatively cheap that are available to me, that somebody's been recommended, or maybe I own them on hand, and I just want to test them first. Okay, we'll say the 3 alternatives are, it's a 12 volt, 300 watt motor with an optimum RPM of 2000. Okay, say that's one motor. We have let's say we'll have a 24 volt motor, and this is going to be a 1 horsepower And this has an optimum RPM of about 500. Okay, and then we've got the 72 volt 2 horsepower motor that has an optimum RPM of 3000. Okay, so those are my 3 different motors. I'm going to go ahead and list this one as 1, this one is 2. Now I'm going to list them as A, B, and C. A, B, and C. So motor A, B, C. Okay, those are my 2 alternatives. That's step 2. Now I'm going to go ahead and draw my table. So for my table, I got zoop, and then I got some zoop, and then I got this zoop, and then I got this, yep. We'll just keep it there for now. So I got this. Now I've got motor A, B, and C. Okay? Just gonna go ahead and draw those up there. I got my issue, which you're supposed to write your issue up above here. So motor selection. In this box here, we list out our criteria. So I'll list out my criteria down here. Over here, we talk about weights. We'll talk about what a weight is. Okay, and then at the bottom, we've got our results. So what are the criteria that I can use to pick a motor? Well, when it comes to motors, what kind of things are important? Well, first of all, you have to mount a motor into it. And that takes a little bit of effort. Is mounting, let's say mounting ease, we'll call it ease of mounting. Is it going to be something that's easy to install in the system? What about gearing? The higher the RPM, or conversely, the lower the RPM of the motor, the more gearing that you're going to need. And if you have more gearing, that means more inefficiency of the system. Okay, so go ahead and draw a line over here. Go ahead and draw a line over here. Let's also say weight. Because this is going to be on a bicycle, you don't want to have a really heavy motor. Okay. Another thing that might be of issue is size. You don't want to have a giant motor. Especially not on a bike. It just becomes cumbersome. And then you can talk about cost of electric support system. If this is a 12 volt system, and this is a 24 volt system, this is a 72 volt system. I could get a converter that goes between 72 and 12 volts. But ultimately, like, what kind of battery am I going to need for this system? Is it going to be a 12 volt? Is it going to be a 24 volt? It's going to be a 72 volt battery. Each one of those battery systems is much different. A 72 volt battery probably won't have as much current draw to produce the same amount of power, versus a 24 volt battery is going to have a little bit more, and a 12 volt battery is going to have the most. If I had a 5 volt battery or 1.5 volt battery, that would be a lot of current. I don't know if I want that. So you have efficiency is another one. Oh, that had nothing to do with what I just said, but you know what? We went there anyways. And what I was just talking about with support electrical. Is how hard is it going to be to go that route? Okay, so this motor is not, it's not all that impressive. Quite frankly, 300 watts is not a ton of power. Less than 1 horsepower, it's in fact half of a horsepower. Oh, I forgot to include actual, like, power here. So lots of things that we can use to judge each of these on. So what we're going to do next is we have to assign weights to these. Now the importance of a weight is, a weight says, here is my relative importance. And I think the way that the book says this is usually for the importance, they will give it some kind of a value, I guess. Never mind. The way I learned it in school was you give it a value 1 through 10, and you rate each of these 1 through 10. Such that, like, if something is a 1, it's twice as important, well, it's half as important to something that's a 2, or it's a tenth as important to something that's a 10. That's one way of doing it. I'm going to go ahead and assign a base weight of about 10. Okay, so 10 is going to be my standard. Then we'll go off of that. If it's twice as important, we'll do a 20. If it's half as important, we'll do a 5. If it's a fourth time as important, I'll do a 2 or a 3. Okay, so here I'm going to go ahead and start with the 10 being important is going to be weight. So here, weight gets a weight of 10. Okay. Now, is size more or less important as far as weight goes? Well, size is less important because you could just move the motor around to get it out of the way. May contribute some to aerodynamics, but I would say it's comparable, but I would say it's also not nearly as much. So I'm going to put that one as an 8. Gearing, also probably not as much. I'm going to go ahead and put that as a 4. It's a lot less than the 10, but it's still important. Ease of mounting, I'm going to say that's probably just as important as your weight, because if it's mounted well, it'll be secure, you'll be able to handle all those forces. It is really important, but maybe not necessarily the most important. Efficiency is valuable. It's something where, yeah, a more efficient system is going to be easier to work with. I'm going to go ahead and say efficiency is probably twice as important as the weight. So we'll give that a 20. Support electrical, how much work is that going to be? I'm going to go ahead and say this is probably a 2. Because electrical components they're pretty cheap to work with and easy to work with. I've had enough experience working with different electrical components that this one doesn't scare me as much, but for somebody who doesn't understand electronics nearly as well, that might be a higher priority. And lastly, power. Giving that one a 25. Because heck yeah, I want a powerful bike. Okay, so that's all it's more than efficiency, it's worth more than everything else. Power is king. So now what I'm going to do is, in the QFD model, what you would do is you would give each of these a score, 1 through 5, or a circle and a triangle, or a circle with a dot, and that would represent a score, and you'd multiply it. That is a valid way of doing it. But for something like this, like, well, I mean, gearing's going to be a little different. What we do instead to make this decision, and it's just a different way of looking at the kind of QFD model, is we're going to assign one of these is going to be a nominal value. Like, it's 1. It's like the same that we did the weights, okay? We picked a weight value, and everything is based on that weight value. We'll get the same kind of feel as we would if we would have written a 1, and this would be a 0.4, and this would be a 1, and this would be a 0.8. We would have gotten the same numbers as a result. So it doesn't matter what the scale is, but it does matter one of these has to be just a regular, this is the de facto one that we're going to compare everything to. And I'm going to go ahead and pick A just because it's the first one, okay? And so what we will say is A gets a 0 score for all of these. Okay, 0 is your baseline. It means that it performs as well as motor A for each of these categories. And then we go and look at the second one, okay? Motor B, it's a little bit bulkier of a motor, a little bit bigger. 24 volt motor is slightly larger. So what I'm going to put for my evaluation, make sure I'm giving this to you correctly, is I'm going to write a positive number if it's better and a negative number if it's worse. Okay, it's a lot like the idea of plus and plus plus. So for mounting ease, well, this is probably going to have about the same mounting structure, as it'll be a little bit bigger, but it's probably going to have the same mounting structure. So that one will be a 0. Okay, as far as gearing goes, okay, this one has an RPM of 500. If you think about it, your bike wheel, if you're using a 26-inch wheel, 26-inch wheel, you're traveling at 30 miles an hour. Quick maths time. I got my phone, which is my favorite calculator. Okay, so calculator. So if it's 26 inches, 26 inches is equal to 2.167 feet. 30 miles an hour is equal to 44 feet per second. Okay, so that means your revolutions per minute, it's doing a total revolution of this times pi. So 44 divided by 2.167 times pi means that you have 6.46 revolutions per second when you're going on a 26-inch bike, 26-inch wheel bike at 30 miles an hour. Okay, so 26-inch wheel bike, 30 miles an hour, that many revolutions per second, which means you have 388 revs per minute, or 388 RPM. Okay, so we have 388 RPM that our cycle is operating at, which is actually really close to 500, which is the nominal speed of this motor. So what I'm going to say is, okay, our cycle at top speed is going to be traveling 30 miles an hour. You're going to be really booking it down the road. The gearing between this and this is actually, it's probably one gear, really. So it doesn't have to be that much. The gearing would not be substantial. You wouldn't have a huge gear ratio to get from here to here. So I'm going to go ahead and say that the gearing on this is a definite +2, really, because it's much simpler. Okay, and here the gearing is worse because you've got now a farther RPM away from this nominal RPM that our wheel is going to be rotating at. So I give it a -1 over there, but I guess we don't need to worry about that one. But I'm going to give it a -1 for mounting too. But, okay, as far as weight goes, both of these are getting a -1. As far as size goes, both of these are also getting a -1. As far as efficiency goes, the higher the motor, the more efficient it's going to be. So this will be a +1 and this will be a +2. Okay, now as far as support electrical goes, quite frankly, a 12-volt system is really easy to work with. There's 12-volt batteries out there. There are also 24-volt batteries out there. There are also 72-volt batteries out there. But if you have any other electrical systems in your bike, trying to go from 24 or 72 down to 5, which is where a lot of control systems are, or if you're trying to also make it something you can plug your USB into, which by the way is one of the design constraints for my system, that is going to be a -1 for both of these. Okay, finally, power. I mean, this one has about twice as much power, and this one has about 4 times as much power, so this one's getting a +1 and a +2. Okay? And now what we do is we then multiply across and sum them down. So here we got 10. This is going to be a -10, -4, that's a -14, -10, that's -24, -8, that's -32, plus 40, That's a positive 8 minus 2. It's a positive 6 plus 50. That's a plus 56. Okay? And similarly down here, well, you know this one's going to be a 0 because they're all zeros. But here you have 8 minus 10. So that's going to be a minus 2. Minus 8. That's going to be a minus 10 overall. Plus 20. That's a plus 10. Minus 2. That's a plus 8. Plus 25. That's a 33. Okay? So there we go. According to this Pugh matrix, we should pick motor C. Mostly just because of this right here. Okay? But, so that's it. We're done, right? We've made our decision. C is the best option. Well, that's a good idea, but now we actually need to try it again as motor C. Doop-a-doop. Because we didn't compare motor B to motor C at all. All we did was compare motor C to motor A. So I'm going to erase all my entries and try one more time. FYI, in the final design of your Pugh matrix that you need to include should include your best option compared to your other alternatives, just like what we're about to do now. But you have to be able to prove that compared to alternative A and B, this one is the only non-negative number. Okay, so now we're going to be 0, 0, 0, 0, 0, 0, 0. Can't draw. We know the final score is going to be 0. For B, mounting ease, well, it's going to be a plus 1 on this. And this one's also going to be a plus 1. And gearing, well, this one's going to be a plus 2. And this one's going to be a plus 1. As for weight, this one's going to be a plus 1. This one's going to be a plus 1. For size, this one's going to be a plus 1. This one's probably going to be a plus 1 too. Efficiency, I'm going to go ahead and give this a 0. And then this one's going to be a minus 1. As far as support electrical, these are both much easier to work with than a 72 volt system. And then as far as power goes, this has less power, this has much less power. Okay, so we go through this now and we calculate all the numbers. So mounting ease, this is a 10. This is an 18. It's 28. 36. 40. This is a positive 15. Okay, and then you got 10, 14, 24, 32, 12, 12, 16, 16 minus 50, negative 34. So comparing these two, now this right here is a big note. I made these efficiencies roughly equal to 0 because there's really not that huge of an efficiency gain between the two. I mean, there is some, but it's not that big. But compared to everything else, it still receives a positive score. So in reality, we would have to go back and evaluate B in regards to both options and be able to definitively prove that B compared to both A and C is the best option. Okay? And then we would be able to say with confidence that we algorithmically determined which one of these is the best. As an engineer, that's kind of a big deal. We like math to make decisions for us. And if we can use this to create math that'll make a decision, this option is better than this option, then we win. A Pugh decision matrix, I've used these before in my private engineering practice. It's something that I would expect you would probably use just in your world at least once or twice, especially if you're making complex decisions between two really good options. A Pugh decision matrix, it does help. Now you may never use this, but I want you to know it because you know what? I'm the instructor and I like teaching how to use math to solve problems. So I'm gonna go ahead and post some SolidWorks videos, keep working on the SolidWorks designs, and I'll be building a shock strut assembly. So be looking for that in SolidWorks. Keep working on your design. I would also suggest getting to work on making some design decisions now using a Pugh matrix, because that's going to be a part of your report. You have to show me that you understand how to do something like this. And then once you have your design all finished, I would expect you to go back and use the QFD, the House of Quality, and evaluate your design as a whole compared to other designs. I'll give you the template for both of these documents as soon as I can. I don't have a template for this yet, but I'll come up with one and I'll share it with the class. So